This video covers section 3.4, the sandwich theorem and some trigonometric limits. Here we're going to learn a new limit technique that helps us find limits for expressions involving trig functions. Or I should say maybe functions involving trig functions. Anyway, let's take a look. Well, you might remember from the last video that we talked about the limit as x approaches infinity of sine of x. And we got that it didn't exist. And why didn't it exist? Well, for the same reason that the limit of cosine is not going to exist, right? Let me actually just expand this out a little bit to remind us all that sine and cosine both oscillate, right, this is y equals cosine of x. And because these functions just keep oscillating forever and ever and ever, they never settle on any one value. So this is one of those weird examples where the limit actually does not exist. And it's not because it's infinite or because the left and right hand limits aren't equal. It's because the function just never converges to a value. It never gets arbitrarily close to a single y value and stays there. It just doesn't. Okay? Next up, we have this limit right here, number 2. And I hope we all can see that this limit is going to be 0, right? Fixed numerator, ever increasing denominator, we should have 0. And in case you're wondering, that function looks something like this. So definitely 0. Extend that a little bit. Now the question is, what happens with number 3? What happens when we combine them? Well, I guess the question is, right, is the limit going to be 0? Is it going to exist? Not going to exist? Is it going to be something else? Well, let's take a gander. Let's see what happens. If I graph this, ignore the bottom two functions there. If I graph it, well, it looks like it does oscillate a little bit, but it also looks like long-term it is converging to 0. So that's good enough for me. I'm going to screenshot this bad boy and say, hey, we've got a limit of 0. I'm not totally sure why, but I guess somehow the 1 over x squared part wins out over the cosine part. Not really a sufficient explanation for, proving that something is true, but it does give us a good intuitive answer. So I'll write that the limit as x approaches infinity of cosine of x over 1 plus x squared equals 0, but I'm going to put a question mark because we're not really sure why. Okay. And the reason that we're not sure is because we can't use the limit laws and the other techniques that we have previously learned. We have to learn something new called the Sandwich Theorem. You may also hear this as the Squeeze Theorem, but this book and many other books call it the Sandwich Theorem, so we will too. I really should have left these blank and let you fill them in. But anyway, you can pause the video and just read this. Probably won't make a whole lot of sense without doing an example, but the basic idea is that if a function is bounded above and below by two other functions that have the same limit, then our function has to have the same limit as well, right? So if we have our function, right, and it does this sort of thing, whatever, and then we have a function bounding it above that kind of does this. I'll try to make that a little smoother looking. And then another function bounding it below that kind of does this. And these functions have the same limit. Well, then this guy winds up getting squeezed in between them, and it's got to have the same limit too. Okay? And this works for limits for x approaching any real number or plus or minus infinity. Very useful. So now we're going to go ahead and solve example 1. So the trick for the challenge for this part is twofold. Number 1, we have to find a lower and upper bounding function for our function, which in this case is cosine of x over 1 plus x squared. And then we also need to show that these lower and upper bounds have the same limit. It's actually not so bad to find some lower bound and some upper bound for the function. It's a little more tricky to do it and ensure that they have the same limit. So what we do, the way we solve this problem, this problem's a little more involved than the other limits, but it is very formulaic. So if you just see how the problem solving goes, then you'll be able to be fine every time, because we basically do the same thing every time. So what we do here is we're always going to start with the trig function. What? Trig function. Okay? And what I mean in that case is we know that, for example, cosine is bounded above by 1 and below by negative 1. Okay? So we're going to start by saying negative 1 is less than or equal to cosine of x, which is less than or equal to 1. Right? We're starting with a trig function because that's what makes this problem complicated. It's the presence of that trig function and that oscillation that we haven't seen before. Now what we're going to do is we're going to simplify, or I shouldn't even say simplify, we're going to mess with the function. We're going to add on pieces until this becomes that. Okay. So at this point, we're just going to divide by 1 plus x squared. We're going to divide all three sides, and you see that we're going to get negative 1 over 1 plus x squared less than or equal to cosine of x over 1 plus x squared less than or equal to 1 over 1 plus x squared. And now you can notice that we are left with the same function that we started with. Now, how does this help? Well, that means that this guy right here is the lower bound, f of x, and this guy right here is the upper bound, h of x. And you can see that this is true. If I go back to Desmos, remember I said to ignore those lower two functions? Well, unignore them, right? The blue one is the lower bound. The green one is the upper bound. And sure enough, that red function, which is our function of interest, is bounded by those two consistently. Right? It is never greater than the green, and it is never less than the blue. So if we go ahead and maybe, crop that appropriately. Sorry about that. Okay, and we maybe stick this over here. Just for some reference over here. Okay, now I'm sticking this to the right because there is still one thing we have to show. We have our lower and upper bounding functions, but we do need to show that their limits are equal. Well, we already did show that the limit as x approaches infinity of 1 plus x squared equals 0. We already showed that. Right? We already showed it. Yay. Okay. So we know that that's true, but if you think about it, the same is true for that first guy. Right? The same, right? This limit is the same as that limit. Right? Because it doesn't matter that the expression is negative. It still has a fixed numerator with an ever-increasing denominator. So now we have a lower bounding function and an upper bounding function with equal limits. So it turns out that our function of interest has the same limit of 0. Okay. So that's our answer. Okay, now let's just do this a bunch of times so that we get this methodology drilled into our brains. First off, I have to make a little correction here, right? Make that an x cubed, or it doesn't quite work out. Otherwise, limit just goes to infinity. Anyway, let's go ahead. We are going to simplify, right? So again, what's making this problem complicated? It's the sine squared part. So we are going to start with sine is bounded by -1 and 1. And at this point, we're just going to square both sides because we don't have sine, we have sine squared of x. Sine squared. So I'll just say, well, actually we have to be a little careful. I'll say square sine of x. Now what happens when you square sine of x? Well, anything squared is non-negative. So we have this. Okay? I like to put a little implies symbol saying this implies that. Okay? Anyway. Now at this point, we need to change, get the highlighter back out. We need to change this into this. Okay? So let's do it. We're going to add 2 to all 3 sides. This will give us 2 less than or equal to 2 plus sine squared of x less than or equal to 3. Next up, we need to multiply by x squared. And that will give us 2x squared, because we do it to all 3 sides, less than or equal to x squared times 2 plus sine squared of x, and then less than or equal to 3x squared. And then we have, I guess we have to divide by x cubed plus 100. Okay, so we have 2x squared over x cubed plus 100 less than or equal to x squared times 2 plus sine squared all over x cubed plus 100. And then this is less than or equal to 3x squared all over x cubed plus 100. And now we have what we wanted. Okay? We have our upper and lower bounds, and all we need to do is ensure that they have the same limits as each other. Well, let's do it out. The limit as x approaches infinity of 2x squared over x cubed plus 100, well, we know that that's going to give us infinity over infinity, never desired. So we're going to multiply the top and the bottom by 1 over x squared, and this will give us the limit as x approaches infinity of 2 over x plus 100, and that clearly equals 0. And similarly, the limit as x approaches infinity of 3x squared over x cubed plus 100. I hope you see it's the same thing, right? We have the same problem. We have infinity over infinity, so I'm squeezing stuff in here. But you solve the problem the same way, and you actually get the same answer, right? Right? So both limits equal 0. Again, just emphasizing with my highlighter here, the limit of this guy equals 0. Limit of that guy equals 0. So then we always write, always, I will take off a point if you don't write this, by, at least a point, by the Sandwich Theorem, the limit as x approaches infinity of x squared times 2 plus sine squared of x all over x cubed plus 100 equals 0. All right, let's look at another example. I think these are our last 2, okay? This one, it'll be somewhat similar, right? We're going to start with our trig function. Now, you might notice that it's sine of 3x. That doesn't matter. The 3 on the inside just affects the period, how quickly sine oscillates. It doesn't actually affect the amplitude, which is how high and low sine gets. So anyway, we do this. We're just going to add 5x to all 3 sides. And then at that point, we're going to divide by x plus 27. Oh, sorry, that should actually be a minus. My bad. But one thing actually I didn't point out, we actually had a negative sign. You can just put that negative sign right there. You just put it in there, right? Because even if we flip the graph of sine, it's still bounded by negative 1 and 1. Okay? Anyway, we have 5x minus sine of 3x, and then we are divided by x plus 27, and then of course on this side we have just see how it's the same thing that we're doing, and of course we now have our upper bound, and we have our lower bound. We have our original function. Yay, that we got just from starting with this trig function. All right, and now we just need to verify. And just be a little careful on this one. Limit as x approaches infinity of 5x minus 1 over x plus 27. Right, we are getting infinity over infinity, so just be a little careful. Multiply the top and the bottom by x. And now don't be on autopilot here. Do the limit out, right? Because if you're on autopilot, you might say, oh, well, look, all of our answers have been 0. It's going to be 0 again. No, it's not. No, it is not. It's going to be 5. That's right. There, 5. Okay. And, well, maybe you can see that if we do this limit as well, limit as x approaches infinity of 5x plus 1 all over x plus 27. Again, similar situation. We have infinity over infinity. And we're going to get limit as x approaches infinity. 5 minus 1 over x over 1 plus 27 over x. And this, in fact, will give us 5 as well. So the limits do, in fact, equal each other. Perfect. So we get to use the sandwich theorem. Oh, did I say? Yeah, I said by the sandwich theorem. Good thing. Okay. By the. Whoop. Try that again. By the sandwich theorem, the limit as x approaches infinity of 5 minus 1 over. Oh, I should say of. Sorry, I should. 5x minus sine of 3x all over x plus 27 equals 5. Not 0, 5. So your answer doesn't always need to be 0. Not only that, x doesn't always need to approach infinity either. Right here we have a limit as x approaches 0. It's a little different. Same thing applies. Same sort of reasoning applies. We're just not approaching infinity. Okay? So same. Now the weird thing is that cosine of 2 over x does one of these things right around the y-axis. So we just need to be a little careful with that, but not really, because it still oscillates between -1 and 1. So we still have this. Right? We still have it. All right, and so anyway, all we do is we multiply by x squared. So what looked to be maybe the most complicated, or just kind of complicated, we're actually done, right? We're done with the hard part. We started with our trig function, and now we ended up with our whole function. And we have our lower and upper bounds to boot. So anyway, we're going to get that the limit as x approaches 0 of negative x squared equals 0, which equals x squared. Oh, sorry, not x squared. The limit as x approaches 0 of x squared. So by the sandwich theorem, the limit as x approaches 0 of x squared cosine of 2 over x equals 0. That's all I've got.